This lesson is on graphing, in particular with using tables. A graph is basically a way of representing all the answers to an equation with two variables. The two variables, for example, could be time and height. In the case of a roller coaster, you could make a graph describing the height of the person as the roller coaster continues on in units of time. Another example with two variables is the following. Say you're at a food fair and they have exquisite items such as Zango juice costing $3 per glass and yam wraps costing $6 each. You have $18 to spend. So the two variables are the number of Zango juices you buy and the number of yam wraps you buy. We could make an equation that would look like $3 per Zango juice and $6 per yam wrap to equal $18 total because that's how much you have. So what are some possibilities given the $18 you have to spend? Well, for example, you could say, what if I bought 2 Zango juice? Well, that would mean x equals 2, which would then mean you could replace it in the equation. Now, remember, if you bought 2 Zango juice, that would cost you $6, which then would leave you with $12 to spend on your yam wraps, which would allow you to spend the money on 2 yam wraps. So you could have 2 Zango juice and 2 yam wraps. That's one possible combination. So a coordinate point for that would be 2, 2. What else? Well, we can see that 18 can be made by 3 times 6, so what if you had 3 yam wraps? So then you'd have y equals 3. So let's replace the y with 3. That would leave us with no money. So we have no more money to spend on Zango juice, and therefore we can buy 0 Zango juice and 3 wraps. So here's yet another coordinate point that came out of this would be 0, 3. Notice I'm putting my x first and my y second. So those are 2 possible points, but there are many more. So let's take this equation and graph out all the possibilities of purchasing combinations of yam wraps and Zango juices with the money that we have. So when graphing an equation, we first want to make a table of values for the independent variable and the dependent variable. So often, x is reserved for independent variables such as time. The dependent variables could be things like height or money, things that depend on the time or on the other independent variable. In this case of Zango juice and yam wraps, one is not necessarily dependent on the other, so we just call one x and call one y. So let's make a table of values. You've already pretty much filled in 2 points. So from the previous slide we had 2, 2. That was shown in the previous slide on how to calculate that. You basically just replace one variable with one guess and then solve for the other variable. And the other option was 0, 3. So those are our 2 options so far. And that's what this states here. The ordered pair solutions that we have found were found by choosing a value for x and then finding the corresponding value for y. Next step is to plot the ordered pair solutions on a coordinate system, so let's try that. 2, 2, 0, 3. We have 2 points representing the number of Zango juice and the number of yam wraps. you can see that the pattern could be continued. So for example, the next number here that should work would be 4 Zango juice and 1 yam wrap. Will that work? Well, 3 times 4 gives us 12, plus 6 gives us 18. It sure does. So these 3 points are probably the best representations here. However, you could combine all of those and make a line. Now, every single point on this line should satisfy the equation. Every single one of them. So this next one here is likely going to be 6, 0. Is 6, 0 going to work? Well, if we replace x with 6, y with 0, 6 times 3 gives us 18, and 6 times 0 is nothing, so therefore it works. Let's continue with some examples. First we have y equals negative 2x plus 1. So let's practice making a table of values. We want to choose x randomly and replace it in the equation and then find the corresponding y. So let's try that out. Y equals negative 2 times something plus 1. So what do you want that something to be? So let's say we chose x to be 1. Let's replace 1. And that gives us negative 2 plus 1, giving us negative 1. So 1 comma negative 1 is an ordered pair solution. Let's try a few others. We have something at 1, and we want our graph to be sort of spread out. So we probably want to choose 0, and we probably want to choose a negative. We might want to choose a bigger number, but you basically want it as spread out as possible and not all tight in one spot. That way you can see what the whole entire graph is going to look like. So let's choose 3. If we stick in a 3, negative 2 times 3 is negative 6 plus 1 is negative 5. Next, we could choose negative 3. If you choose negative 3, you'll have negative 2 times negative 3 is 6 plus 1 is 7. So negative 3, 7 works also. Let's just try 0 and see what happens. If we stick in a 0, that'll give us 0 plus 1, and that gives us 1. So we've got a bunch of points. Let's plot them and connect them and see what the pattern looks like. 1 comma negative 1, 3 comma negative 5, negative 3 comma 7, and that's off our graph, so that's a little more difficult, and 0 comma 1. So you can almost see this pattern here of points lining up, and you can pull out a ruler and connect the points. Every single one of these points on this graph should satisfy this x and y pair. There's an infinite number of those possible answers, and so that's how we can represent it exactly, is with a graph. Let's try another example. Let's give it a go. This here we have an absolute value. So let's try a little bit at every spot. So let's try one maybe at 2, at 0, at negative 2. And I'm choosing them randomly, just basically to make it as spread out as possible. Stick in a 2, you get 2 minus 1 is 1, absolute value of 1 is 1. Stick in a 0, you get 0 minus 1, absolute value of negative 1 is also 1. Stick in a negative 2, that'll be absolute value of negative 3, which is 3. So let's plot those points. 2, 1, 0, 1, negative 2, 3. Well, these don't really form a line. However, let's continue checking some more points. What would happen? Maybe let's check at 1. I'm wondering about 1 because it is where this pattern is breaking. So let's try and stick in a 1. If you stick in a 1, I'll just replace it here. What would that give us? If you stick in a 1, 1 minus 1 is 0, absolute value of 0 is 0. So 1 comma 0 is there. Okay, so you may notice a pattern already forming, but you may want to check more points. Eventually you'll have intuition to guide you through this and to notice that every time you have an absolute value, your graph will look like a V. And it could be an upside down V, a sideways V, it could be, your graph will look like a V. Let's continue. Here's another type of graph. It has a square. So let's look at what a square type graph looks like. We might need more examples because it's likely not going to be linear. You'll notice when there's something funny with the x, you aren't going to get a line. So let's try a bunch of points here. So maybe -3, -1, 0, 1, 3, 5, just for kicks. So try it all out. And how about we do this? I'll write it out once, but then erase it. So let's say we stuck in a -3. What's that going to give us? That'll be a 9 minus a 2, which gives us 7. If you have a whiteboard, this process is nice and easy as well. Stick in a -1. -1 squared is 1 minus 2, gives us -1. Stick in a 0. That'll give you 0 minus 2, which gives you -2. Let's replace the x with a 1. So that gives us 1 minus 2, which is -1. What if you stick in a 3? 3 squared is 9 minus 2, gives us 7. Notice that -3 and 3 both gave you 7. So there is some symmetry going on here. Alright, and last one, let's try a 5. So that would be 25 minus 2, which would be 23. Now this one is probably too big to graph, so let's not graph it. So we get -3, 7. So that's about there. And 3 also gives us 7. -1 gives us -1. And 1 gives us -1, and 0 gives us -2. We might want to check these points at 2 and -2, so let's try 2 and -2. So if we stick in a 2 for x, here, continue it here, we get 4 minus 2, which is 2, and stick in a -2, you'll notice that's also the same thing. So 2 gives you 2, -2 gives you 2 as well. You'll notice it's forming a U shape. And you could continue. You could even stick in smaller numbers such as 1/2. What would happen? Would it fill in the pattern? Well, if you stick in a half, so try 0.5 squared would be 0.25 minus 2, which gives you -1.75. -1.75 is about here. That would be the same as if 0.5 was negative. So you'll notice eventually it starts forming this curve. And this is actually called a parabola. Let's try the next graph. This one is a cube. So when you have a cube, very likely that is not going to be a line because there's something affecting the x, some odd thing like a square or an absolute value, etc. So let's try a bunch of points here, -3, -2, -1, 0, 1, 2, 3. You basically want to center yourself around the middle to check it all out. So we're just going to cube each thing. So we go to -3 cubed. You'll notice that 3 negatives make a negative, and 3 cubed is 27. That is too big to graph, so this point will be very difficult to graph, and so will this one, because you'll notice if y is 3 cubed, it's the same number but no negative. So this will also be too big to graph. Let's continue. What if we cubed -2? That would also stay negative, and 2 cubed is 8. Cubing -1 would stay as -1. Cubing 0 would stay as 0. Cubing 1 would stay as 1. Cubing 2 would give you 8. Let's try to plot those. So -2, -8. That's very low, way down there. And so is 2. 2, 8, that's way up here. So everything's really happening in this little part here. It seems like the graph is escaping. Okay, so 0, 0 is a point, -1, -1, and 1, 1 is a point. You'll notice this is a cubic function, and it's got this sort of shape to it. Sometimes it's nice to even get the smaller numbers. In, so you could check 0.5 with the calculator, -0.5, etc. You'll see that it's not jagged, it's nice and smooth. Alright, what about these ones? What if you had just y equals 1? That's all they give you. Where's the x? There's no x. X is absent. Yikes, what do we do now? Well, that means we can assign him to anything. Meaning, in our table of values, as long as my y value is 1, I don't really care what x is because it has not been forced into being anything. I don't really care what x is because it could really be anything. It's not there to claim its prize. So -3, -2, 0, 1, 2, whatever. So for every x value, your y value is 1. You can imagine that to be filling up this nice horizontal line. What if x is -2? So y is absent. And that also means it can be anything. So in your table of values, as long as your x is -2, I don't really care what y is. Whatever. So as long as your x value is -2, all the possible y's can be used. And that gives you your vertical line. Let's talk a little bit about what makes an equation a line, a linear equation. Well, you've got these two forms. You may have noticed with the graphs that we have been making, the ones that had x and y values just plain with no squares, no cubes, no absolute values, they were forming lines. They were linear. The other ones were not. They were curvy. So you usually have a linear equation given in one of the two following forms, either in standard or general form, both terms are used, or a slope-intercept form. We will soon find out why it's called that way in the next upcoming lessons. So you also have x and y intercepts. So this is a key concept because it helps you graph equations in general form when you find the x and y intercept. You may also be asked to find the x and y intercept at any point. So let's talk about how that happens. So you had a random line, totally random. The x-intercept is the point at which the graph intersects the x-axis, right there. So that's the x-intercept. And the point at which the graph intersects the y-axis is the y-intercept. Now, how would you find these points? These points are basically formed, you'll notice if it's crossing the x-axis, that means your y value has to be 0. So what you can do is you can just plug in y with a 0 and find your x. Same thing goes for the y-intercept. The y-intercept is found when the x values are 0. So you would do the same thing. Similarly, you could plug in x to be 0 and find your y. They're nice and useful when using, when graphing standard or general form, because they give you nice points to start off with. Let's look at some examples of that. So say you had an equation like this. It is currently in slope-intercept form, which was y equals mx plus b. The y is by itself and the x is integrated into the rest. They want you to rewrite it in general form and then use the x and y intercepts to graph it. So let's try that. So if we've got y equals negative 2x over 3 plus 6, and we want to get that back to general form, which was ax plus by equals 0. So let's get everything over to the left. So first we want to get rid of this fraction. Let's get rid of that fraction. So multiply everything by 3, which gives us 3y equals negative 2x plus 18. Let's bring the x and the y over. So we have add 2x to both sides. Oops. Giving you 2x plus 3y equals 18. Now this is your general form. You'll notice this had a 0 here, but this could have been any constant c. So let's figure out our x and y intercepts. X-intercept is found when you let y be 0. So let's try that. 2x plus 3 times 0 would be 18. So let's find our x. So 2x equals 18, giving us x equals 9. Therefore, when x is 9, y is 0. That is one pair. Let's find our y-intercept. So let x be 0. Therefore, 3y is 18. Therefore, y is 6, giving us the y-intercept being 0, 6. 9, 0 is right there, and 0, 6 is right there. You can connect your 2 points, and voila, you have a line which represents this equation. Here's another example. Here we have something written in general form, and they want us to write it in slope-intercept form. Notice again that this could have been written as x plus 2y equals 6 as well. I'll consider both as general form because the main idea is that the x and y are on the left-hand side. Whereas slope-intercept form, you want y equals by itself, so you want the y variable on its own. Those are just two different formats, and you'll notice that rewriting them between one or the other is useful because sometimes one is easier to graph than the other. Sometimes one is easier to manipulate than the other one. Sometimes one is easier to find coordinate points for than the other. So let's try this one out. We have this equation and we want y by itself. So let's subtract x from both sides and let's add 6 to both sides. So that gives us 2y is equal to negative x plus 6. To get y by itself, you want to divide every single term by 2, giving us y equals negative x over 2, which also could be seen as negative 1/2 x, either way, plus 3. So let's use a table of values to find some points. So here, you'll notice that you want to choose your x carefully. If you chose a 3, you'll have to go 3 times a half, which you can do, you just have to use your fractions. So you likely would want to choose something that will cancel the 2. So let's choose 2, maybe a 0 and a negative 2, because we want our graph to be nicely spread out. So we'll have a point here, here, and here. So if we stick in a 2, what do we get? 2 times negative a half gives us negative 1 plus 3 gives us 2. If we stick in a 0, that gives us 0 plus 3 gives us 3. Notice this is actually the y-intercept. And let's replace the x with a negative 2, and that gives us 1 plus 3, which is 4. So you've made a table of values. Let's plot some points. You've got 2, 2, 0, 3, negative 2, 4. So you can start seeing the pattern, and you see that that line will describe all the possible points that satisfy this equation. One more example for you. Here's a bit of a word problem. But however, it's not very much different. You just basically have to write the equation first before you do any graphing. So here's I think this one's a little dated, but let's check it out. Each semester, college charges a service fee of $50 plus $25 for each credit taken. Write a linear equation that gives the enrollment cost, so you want cost equaling, for the student taking N credits. So you pay $50 regardless, and then you pay $25 times the number of credits. And N is representing the number of credits. So that's really all you need to do with the word part. Now you want to be able to graph the relationship. So you'll notice it starts with $25. So let's just look at, okay, what if a student is taking N credits, so 1 credit, what would happen? Notice N is kind of your input, so it's your independent, and your cost is depending on your independent variable, which is the number of credits. So your X should actually be your N, which is independent number of credits, and your Y should really be your cost, which is depending on the number of credits. Okay, so if you were taking 1 credit, you'd pay $50 plus the $25 for 1 credit, which would be $75. If you were taking 3 credits, you'd have 3 times 25, which is 75, plus 50, which is 125. So now you'll notice your scale probably skips by 25s. So let's make our scale go, for number of credits, we just want 0, 1, 2, 3, 4, etc. And for our cost, we probably want it to skip by 25s or even 50s, but let's just do 25s here. So I don't think we can go any higher on this graph with this scale. You might have to change the scale if you want it to go bigger. So 1 would be 75. Notice 0 credits would be 50, because it's a little silly to say that, but if you weren't taking credits but you signed up to be a student, you'd pay $50. And 3 credits was 125. So you can see through the pattern that 2 credits was probably $100 without even doing any calculation. So every single point here will represent a value for the number of credits that is chosen.